Now we're going to talk about the algorithmic price you pay. And this is our introduction to Big O notation. But what is Big O notation? Big O is how software engineers describe how efficient an algorithm is. It is a way to measure time, or how long does it take to finish, and space, how much memory does it use. Big O doesn't care about the exact time, like 2 seconds or 3.5 MBs of RAM. Instead, it helps us understand how the algorithm behaves when things get big, like 1,000 users or 1,000,000 search results. And we write Big O like this: O of 1, or O of n, or O log n. Each one means something different, and we're going to walk through the most common ones using examples from real apps you've used before. We're going to start with O of 1. What this means is that this is always fast, no matter how much data there is. A good example is when you tap the profile icon in YouTube. Because you have a user ID, the app instantly shows your profile info. Even if YouTube has 10 users or 10 million users, it doesn't matter. It just grabs your data directly. Think of it like looking something up in a specific spot. You don't need to search. You just go straight there. And this is the gold standard of speed. Now we're going to talk about O of n. And this means it slows down as the amount of data increases. A good example from real software is when you use the search bar in Gmail and it checks every email to find a match. The more emails you have, the longer it takes. And this is called linear search. If you have 100 emails, it looks at 100, and if you have 10,000, it checks 10,000. So keep this in mind when you see O of n. More data means it takes more time. Now let's look at O log of n. And this means gets faster by cutting the problem in half each time. So when you search for a product on Amazon, the system doesn't check everything. It uses filters, categories, and indexes to quickly narrow down your results. This is what engineers call binary search or divide and conquer approach. It's incredibly efficient for large data sets, like the billions of items Amazon handles. Now we're going to talk about O of n log n. First, organize everything, and then search fast. So let's look at an example in Google Photos. Google Photos sorts your pictures by date before showing them on a timeline. It takes a bit of work up front to sort them, but once sorted, everything else becomes faster. This is the fastest known time complexity for general sorting, and it's used by apps when they need to both scale and stay organized. Lastly, in time complexity, we're going to talk about O of n squared. I like to call it O no. And it means it compares everything to everything. And this one gets slow very fast. An example is, imagine a recommendation engine that compares every user's watch history to every other user in the app to find similar tastes. If you think about it, that's a lot of comparisons, right? Because if you have 100 users, that means 10,000 checks. If you have 1,000 users, that jumps right to 1,000,000. And keep this in mind. Most modern apps avoid this unless the data set is small or tiny, or the comparison is absolutely necessary. So now that we have a handle on the different time complexities, let's answer the question, why time complexity matters. So let's say you're building a video app like TikTok. If your code is slow when a user has 100 videos, well, imagine what happens when they have 1,000 or 10,000. Poor time complexity means long waits, frozen screens, and annoyed users. And good time complexity means instant responses, happy users, and 5-star reviews. Now let's turn our attention to space complexity, or how much memory does the algorithm use. So for this one, we also have O of 1, but this one means that it uses a fixed amount of memory. A good example here is Slack. So in Slack, you might just see if you have any unread messages. This is simply yes or no. It doesn't store extra data. It just looks and answers. So it doesn't matter how many messages you have. It doesn't take any more space to let you know, hey, you have messages. Next, we have O of n. From the space complexity standpoint, it means memory usage grows with your data. A good example is Spotify downloading songs to your phone. Clearly, if you download 5 songs, it uses space for 5, and if you download 500, it needs more storage. The lesson here is that the more input, the more memory it needs. And lastly, we're going to cover O of n squared, which in the context of space complexity means memory grows very quickly as the data grows. Now imagine if an AI in Netflix tried to create a huge grid showing how every show relates to every other show. The memory usage would explode. That's why smart systems look for shortcuts or smarter data structures. In business terms, we have a comparison of the complexity type, what it affects, and what it feels like. So you can study this in your own time, but just keep in mind the few lines that we have here at the bottom. The faster and leaner your algorithm, the more users you can serve with less cost. Remember, good engineers write algorithms that scale, and great engineers write ones that scale gracefully.